In this lecture, we're going to talk a bit more about the process of electrolysis. Recall that voltaic cells are electrochemical cells that create electrical work from chemical energy. On the contrary, electrolytic cells use up electrical work to power unfavorable redox reactions, such as decomposition reactions. Now, we already spoke about the decomposition of molten sodium chloride. Now we're going to talk about the decomposition of aqueous sodium chloride. And this guy is a little bit different because our solvent is water. When we spoke about molten sodium chloride, we didn't have any solvent. So, let's see how our solvent, namely water, affects our reaction. So first, let's look at our electrolytic cell. So in this cell, we have a battery, a voltaic cell that powers our reaction. And it powers it by sending electrons this way. So that means this electrode will collect these electrons, making it negatively charged. At the same time, this electrode will lose electrons, making this guy positively charged, because electrons want to flow from this guy to this guy. So, let's look at our solution. Within our solution, we have a bunch of sodium ions dissolved and chloride ions dissolved. The positively charged ions will be attracted to the negatively charged electrode. So a lot of the sodium ions will move to the left side, next to this negatively charged electrode. Likewise, the negatively charged ions will move toward the positively charged electrode. So all the chloride ions will collect next to or on the right side. So anytime this positively charged sodium ion hits this negatively charged electrode, a transfer of electrons will occur. So a sodium ion will gain electrons, and that means it's reduced. And by definition, wherever reduction occurs, that's our cathode. So this side of the cell is our cathode, and that means this side of the cell is the anode, because that's where oxidation takes place. The chloride ions are oxidized and lose electrons, and these electrons jump onto the electrode and travel on to this way, thus creating a circuit that moves in this direction. Now that we know what our layout of our electrolytic cell is, let's talk about the oxidation and reduction reactions. Now, when we spoke about molten sodium chloride, only one oxidation reaction was possible and only one reduction reaction was possible. But now we're in the presence of a solvent, namely water. So water is also capable of undergoing oxidation, and water likewise is also capable of undergoing reduction. So let's look at oxidation first. So what atoms are able to oxidize? Well, this atom can oxidize, and a water atom can oxidize. Now, if this atom decides to oxidize, this is our oxidation reaction. Now, if water decides to oxidize, namely the oxygen decides to oxidize, then this is our oxidation reactions. How do we choose which one occurs? Well, the one that's more negative, the one that's lower on the reduction half reaction table, that's the one that is more likely to undergo oxidation. And since this guy has a more negative cell voltage, that means this guy is more likely to undergo oxidation. And so this will be our oxidation reaction. Likewise, let's look at reduction. We have two possible reactions for a reduction. Now, our sodium ion could be reduced into sodium solid, or our water molecule could be reduced into this guy. Now, let's look at which one is more likely to occur. Now, for reduction, it's the opposite. The more positive it is, the more likely it is to occur. So whatever is higher up on the reduction half reaction table, that guy will be more likely to undergo reduction. So since this is more positive, that means this will be our reduction reaction. So now we must add up all these reactions except this one, because this one won't occur, this one will occur, this one will occur, and this one won't occur, and that means we're still going to have these atoms found in our solution. So we add this guy up, and this guy up, and we get the following net reaction. So when this guy and this guy react, they will create sodium or salt within solution, plus 2 molecules of water in a liquid state will produce diatomic gas, plus another diatomic gas, plus this 2 hydroxide in the aqueous state, and 2 sodium molecules in the aqueous state. We also add up these cell voltages, and we get this following cell voltage. So this is the amount of energy, electrical work that needs to be put in by the battery to power this reaction. So we see that decomposition reactions require work. Well, why? Well, that's because they're unfavorable redox reactions. So that's the difference between molten sodium chloride and aqueous sodium chloride. In molten sodium chloride, the solvent wasn't present, water wasn't present, and so there was only one oxidation and one reduction reaction. In aqueous sodium chloride, there are 2 possibilities for oxidation and reduction, and you have to look at their cell voltages to choose. For reduction, you choose the one that's more positive or less negative. For oxidation, you choose the one that's less positive or more negative. That's exactly what we did here.